The title of my poster is Unconditionally Secure, Relativistic, Multi-Party, Biased, Coin Flipping and Die Rolling. It is based on this paper. I would like to thank the organizers and committees for organizing Qcrypt 2022 and for the opportunity to present my work here. I would also like to thank my funder, the UK Quantum Communications Hub. Coin flipping and multi-party die rolling cannot achieve unconditional security with non-relativistic quantum protocols. However, Kent showed that two-party unbiased coin flipping can achieve unconditional security with relativistic protocols. In this work, we extend Kent's protocol to arbitrary number of parties and arbitrary number of outcomes for any chosen outcome biases and show our protocols unconditionally secure. Our results prove that the most general random secure multiparty computation, where all parties receive the output and there is no secret input by any party, can be implemented with unconditional security. Our protocols do not require any quantum communication and are therefore practical to implement with current technology, and also, to our knowledge, are the first multi-party relativistic cryptographic protocols. In a die rolling protocol, m parties agree on the number n of possible outcomes and on the ideal probability distribution for the outcomes. The protocol must satisfy correctness and security, which are defined as follows. Correctness is the property according to which all parties agree on the outcome when all parties follow the protocol honestly and no party aborts. Security means the following. For all k, when the k party follows the protocol honestly and no party aborts, the outcome O is obtained with a probability that is very close to the ideal probability PO defined by the task, as given by some security parameter delta for all outcomes O, where if delta is 0, we call the protocol ideal. If delta tends to 0 by increasing some security parameter, we call the protocol arbitrarily secure. Our protocol works because we implemented in some spacetime setting that will allow us to use the principle of non-superluminal signaling to prove security. So first, the parties define a reference frame. In this frame, they define non-intersecting balls with the property that their distances are sufficiently large, and they define time intervals sufficiently small to satisfy this property, which basically says that time signals leaving ball BI cannot reach any other balls within the time intervals Ti, if these light signals are traveling at the speed of light through vacuum. This is the crucial property that will allow us to show the security of our protocols. So, the Kate party has laboratories in all balls. As we can see in this example with 3 parties, the first party has laboratories given by the blue boxes in all balls. The Kate party does not need to trust the location of the other party's laboratories, but he must guarantee that his laboratory LKI is within the ball BI during the protocol. Before implementing the protocol, the parties agree on some parameters. Parameters n, subsets omega O of the set of integers with n numbers, positive parameters and small parameters alpha and epsilon, k for all k. The parameter epsilon k provides the experimental uncertainty of a random number generator Rk of party k. And alpha must be made arbitrarily small by making n arbitrarily large, so that the number of elements of the set omega O divided by n is very close to the probability P(O) in the ideal outcome probabilities defined by the task. The security parameter delta is defined by this and must be made arbitrarily small to satisfy security, which can be made by making alpha very small, meaning by taking n very large, and also by making the uncertainties of the random number generators very small, which is possible using the piling up lemma. So the protocol has three stages. In the predistribution stage, each party sends a message to the laboratories, to his laboratories in the other balls. So for example, in the case of m equal 3, we see that party 1 has blue laboratories, and in the ball B1, he generates in his random number generator a message M1, which he transmits through secure and authenticated channels to his laboratories in the other two balls, and similarly for the other parties. This can be arbitrarily in advance. So this is not a fast step. In the relativistic step, then we have that each party must transmit messages very fast to the nearby laboratories of another party. As we can see, for example, in ball B1, parties 2 and 3 send messages very fast to the laboratory of party 1. And similarly in other balls with other parties receiving the messages. The K party does not abort only if it receives the message of the corresponding size not after the time tk. So this will allow the protocol to satisfy security using no superluminal signaling. Then in the verification protocol, the parties verify that they receive the same messages by the other parties. Otherwise they abort. If they don't abort, they agree that the outcome is I if the message, if the string, if the number x belongs to the set omega I, where x is the sum of all the messages mk modulo n. It is easy to see that the protocol is correct, and the security is shown for arbitrary quantum cheating strategies. It follows from the spacetime setting of the protocol and the principle of no superluminal signaling. Our protocols have some advantages over quantum non-relativistic protocols. First, they achieve unconditional security with arbitrarily small delta. They also do not require quantum communication and therefore are free from various experimental challenges. The distance among parties can be made very large in practice, which is very challenging with quantum protocols. They also trivially implement weak die rolling with unconditional security. But they have some important challenges. Some steps must be very fast to achieve spaceless separation, but this is feasible with field programmable gate arrays as shown by previous relativistic cryptography demonstrations. They also need the laboratories to be synchronized securely, which can also be implemented as shown by previous demonstrations of relativistic cryptography. Our protocols are intrinsically classical but can be made quantum using quantum random number generators, which is ideal so that the parties can guarantee that their inputs are truly random. Additionally, quantum key distribution links can be used to expand the secure channels among the various laboratories. This can be implemented in quantum networks and quantum internet. With this, I would like to thank you for your attention.